enough right there. All right. So what I'm going to do is I'm going to draw my two metals. And again, I could probably even decide what metals those are because, wow, that metal wants to be 3 plus. Huh. How many metals over here want to be 3 plus? Not many. Probably aluminum is probably the metal that we're talking about here. But nonetheless, it doesn't really matter. So I have a 2M sub S, meaning it's the metal, solid, okay, plus 3 chlorine, 2 gases, goes to 2 MCl3 solids, okay? So it's probably aluminum chloride. Now, with that, that tells me that my overall equation has to equal that. So how am I going to manipulate these other equations to cancel out and get that? That's all I'm looking for. So when I look up here, the very first equation has 2 metals plus 6 hydrochloric acid aqueous going to 2 metal chlorides plus hydrogen gas. That one actually looks fine. Why? Because I have 2M here, so I should have 2M here. Right? I want my 2M here, so I have 2M here. I don't want 2M over here, because that would give me 2M here as a product. It's a reactant, so that one's fine. So let's do 2M. Just leave that one for now. Let's just draw it in. Solid plus 6 hydrochloric acids, aqueous, goes to 2 metal chlorides, solid probably, or no, aqueous. Hey, there's something a little different than our product. Plus 3 hydrogen gases, and I know that the enthalpy of that is negative 706.0 kilojoules. Okay, are we tracking? Cool? So here's what that tells me. That 2 metal solid is that 2 metal solid. It means that probably I have no HCl in here, so probably have to figure out how to get rid of my HCl's. It also tells me that I have 2 metal chlorides aqueous. I need metal chloride solid. So probably have to do something to get solid, not aqueous. And I don't have any hydrogen down here, so I probably have to get rid of hydrogen somehow. So I'm going to look at my next equation down, and I'm going to look at this and go, oh, well, that's kind of cool. I've got hydrogen chloride or hydrochloric acid gas here, and I've got hydrogen chloride aqueous here. I like that because hydrochloric acid aqueous here cancels with hydrochloric acid aqueous here. So I like the way that equation's set up too, so I'm going to leave that one as is. So my next equation is HCl gas goes to HCl aqueous. That's kind of cool. And I know my energy associated with that is negative 74.8. Okay, kilojoules per mole. That's all per mole. Are we following what I'm doing here? I'm just walking through to see how I'm going to get rid of, cancel things out to get that overall reaction. Now, I'm already telling you I'm probably going to have to manipulate this one farther because I see 6 here and I only see 1 here. But I'm going to leave that for now until I get my equations correct. Are we tracking with that? Okay. Now I'm going to go down to my next equation and say I've got hydrogen gas plus chlorine gas. Well, let's look at what I've got down there. I still don't have hydrogen and chlorine, so that whole equation's going to go away. But what I like about the way that one's set up is I've got hydrochloric acid gas over here, which tells me that's probably going to cancel with my hydrochloric gas here. So I'm going to leave that one as is as well. Does that make sense? Not only that, but I like having hydrogen over here because I have hydrogen over here, so that's going to cancel. So I'm going to leave that one as is. Hydrogen gas plus chlorine gas goes to 2 hydrochloric gases. Okay? So far, so good? All right. My last one, I'm going to look at and say, okay, now this is where I have my MCl3 solid. Huh. Yeah, good. This one has my MCl3 solid on the left. I need my MCl3 solid on the right. Oh, sorry, I didn't write the enthalpy of that one. Negative 184, 1845, 0 kilojoules. Okay. So this one, this fourth equation has my metal chloride on the left as a solid. I need my metal chloride on the right as a solid, so I have to flip that one. So I'm going to flip that. So MCl3 aqueous goes to MCl3 solid, but notice my enthalpy is negative 305. So what do? You got it. That's exothermic, this one's endothermic. That's all I'm going to do. So now I've got 305.0 kilojoules. Any questions what I've done so far? Now my equations are correct. Now I have to work with my stoichiometry in order for things to cancel. So when I look at this, I've got 6 hydrochloric acids here as aqueous. I need a lot more hydrochloric acids, don't I? How many more? 6 more. So here's what I'm going to do. I'm going to use a different color pen on this. I'm going to take 6 and 6, which means I need to do what over here? Times 6. Are we tracking what I just did? Okay. So that gives me this and this cancel, right? But here's the thing. I go to the next equation, and I have 2 HCl gases, and here I have 6 HCl gases. I know that this cancels. That's great, wonderful. But these don't cancel, so what do I need to do? Multiply this equation by 3. So I'm going to have 3, I'm going to have 3, and I'm going to have 6. Are we tracking? Which means I need to do that. Right? Okay, so now I look at this equation, and I think, oh, that's kind of cool. So 6 HCl gases, 6 HCl gases, that cancels. Not only that, but notice, I also can cancel out my hydrogens. Hydrogen gas cancels with hydrogen gas, because I have 3 on the left, and I have 3 on the right. How are we doing so far? Good? Are we done? No, we're not done. I've got 2 metal chloride aqueuses here. I only have 1 metal chloride aqueous is here, so what do I need to do? Multiply it by 2. So this one goes 2, this one goes 2, this one goes 2. Then I can cancel out that, and lo and behold, I have 2 metal solids plus 3 chlorine gases goes to 2 metal chloride solids, exactly what the question's asking. Tyson, is that a confused look, or is that a, I can't really tell because I can't see your face, but your eyes look like you were. Ish. Ish, okay. And again, these are just problems of thinking through what do I ultimately want to get out at the end? And what have I been given in form? This is Hess's law, by the way. That's all we're doing, okay? If I don't know how to get from here to here, but I do know these, then I can add these up or modify these in a way to get them. So in the end, all I'm going to do then is take my calculator, my trusty dusty calculator, and I'm going to bring my glasses, so it's going to be even more difficult. I'm going to, okay, so I'm going to take negative 607. I'll bring that down over here. So negative 706.0 kilojoules. I'm going to take 6 times the negative 74.8, so 74.8 times 6 equals a negative 448.8 kilojoules. Then I'm going to take my next one down and look at it and go, oh, I've got 3 of those. Yeah, a lot of those. So 1845, 1845 times 3 equals negative 5,035 kilojoules. And lastly, I'm going to take my endothermic one, 305, multiply it. Actually, no, that one, that's called 610 kilojoules. That's really difficult math there. So now what I'm going to do is I'm going to just add all these together. So I'm going to find my inversion. There it is. So I'm going to add 610. I'm going to subtract 448. And then I'm going to subtract 706. And if I do it, I get a negative 6,079 kilojoules, and probably round that to 3 significant figures would be fine, but I'm going to leave it at 4. Okay. So when I take a metal plus chlorine gas, it's an exothermic reaction, meaning chlorine really wants aluminum's electrons. How much does it want them? By 7,000 or 6,079 kilojoules. So if you put an aluminum metal and you bubble chlorine gas over it, it will be violently explosive. Okay? Because that's a very exothermic, heat-giving reaction. Cool? Okay. Hopefully that dissonant chord just resolved. If not, definitely spend some time working these problems, because these are really the Hess's law problems. Okay? Good? I hope. All right. All right, so that's it for chapter 5. Chapter 5 is in the book, so to speak. And I guess the homework due what, Sunday night? So I took out some of the real difficult ones, because sometimes these thermal problems can really bog down and get kind of gory. So I think I removed like 11 from that assignment that just were taking you into a concept that probably only 3 of you in this class are going to need with Dr. Harris. So I didn't want to take the rest of you through the beauty of resolving those. So I jettisoned them to make it a little bit more doable. Okay? So we're moving into quantum. I love quantum. Do I believe in quantum? Maybe. Right now it's the best theory that we have. Is it the right theory? Probably not. But it works. So we believe it, and we study it, and we throw a lot of money at it, and we all learn it. And we learn it as S's and P's and D's and F's, and that's cool. But what really I think is fantastic about this is we get to look at photons and the photons' interaction with electrons. Now that's really cool. And the reason why that's cool is because we live in an electron universe. We live in a universe where all we're seeing right now with our little beady eyes is the excitement of photons and electrons working together. We're colors, like that beautiful yellow right there, the beautiful blue, that blue right there. It's the way that the photons are exciting the pigments within, probably that's probably a polymer, that's probably cotton. But the way the polymer has absorbed those organic molecules and they're vibrating frequencies that our light picks up as color. It's amazing that we have a colored universe, by the way. Because the electromagnetic spectrum that is color is very, very, very narrow. And that our eyes can actually pick that up, our photons, the retina. In fact, you want to see how that works? Let me show you this. This is the coolest thing. Just because it's fun to geek out every once in a while, and why not? I mean, we're in a science class, so let's learn this stuff. So when you look at what's going on, when you actually look at what's going on in color, the way our eyes actually perceive this, and one of the things I find super fascinating, a great conversation to have around the dinner table with my kids, I always ask them, is the universe an innie or an outie? And here's what I mean by that. This is a really important fundamental question. Because when we see objects, our brain has to reverse them, because when they come in, they're upside down, they're inside out. And our brain corrects that. But my question is our brain correcting that, or is the universe actually an innie, not an outie? That's an interesting question, if you actually think about that. Because if my brain is correcting what I think I'm seeing, maybe I'm not really seeing it, maybe it actually is an internal universe, not an external universe. Kind of an interesting question. But with that, how does my brain actually perceive what I'm seeing? How do I actually look out and see bricks and see students and see a clock and see chairs and things like that? How do I actually see that? Here's all that's going on. It's pretty remarkable. We have a molecule in our body. Some of you, and again, we can geek out on this as much as you would want. But what's happening here is we basically have this molecule within the body that looks like this. And the reason why I think this is so fascinating is because our body, that's the molecule right now. Some of you have probably heard of it if you had a biology course. It's called retinal. Okay? This is transretinal. So what's happening with transretinal is this bond right here is super special. Transretinal, through enzymes, isomerizes to cisretinal. Hang on a second. I got my geminal methyls. I typically don't draw this. I draw this upside down for this class. I'll put my geminals in. So with this, you can see that my body then takes this molecule and flips it. So what happens here is I go from what's called cis to trans. And this goes back through photons, or photochemistry, which is what we're going to be talking about. So the way I actually see is that the cis-retinal within the proteins and the enzymes of the body, within my rods and cones of my eye, they actually accept a photon. A little photon comes in, it flips it to a trans, and because this is connected to a massive protein, it then triggers another protein mechanism that tells my brain to make that image. And that's how you see it. Now here's the cool thing. It takes time for the enzyme to convert the transretinal back to the cisretinal. So if you ever stare at a really bright object and then you close your eyes, you can still see the object. Why? Because you've consumed the cisretinal and you've converted it to trans, and it takes time for the trans to go back to cis. Over time, it does reload, and the image goes away, and now you can use that part of your eyes again. So what we're talking about here is we're talking about the interplay of photons and electrons. And that's why I think this chapter is fascinating. Because if you think about this, we started this entire semester talking about how the periodic table isn't some mystery. It's simply a way of counting from 1 to 118. And so what I love about this chapter is this chapter deals with where do those electrons go. Electrons like to go. Bases always attack acids. Lewis base are a pair of electrons that go attack something. But the question is, where are the electrons? So if I look up here on these blue numbers, I know beryllium has 4 electrons. I know calcium has 20 electrons. I know my favorite atom has 6 electrons. And bromine has 35, and krypton has 36. And if you get bigger down here, Seborgium, who I've actually met right here, has 106. Right? He was the only person, by the way, who was named an atom or element while he was still living. So like Einsteinium and Fermi and all these other ones, they were dead. Glenn Seaberg, was a particle physicist at Berkeley. Coolest thing, when I was a postdoc there, the organic chemistry building was a 9-story building, and you had to have a special key to get from, first 2 levels were just basically undergrad teaching classes. 3rd level and above was all the advanced research and stuff where I was in my postdoc. And I forgot my key, and I was like, ah, crap. So I went into the elevator, I was coming back down out of the elevator, and guess who steps on the elevator? Element 106. I could not believe it. Glenn Seaberg hops on the elevator. I'm dumbfounded. And he goes, hey, young man, where are you going? I said, well, I'm going back to my dorm or my house to get my key because I can't get up to Dalvin's lab. He said, oh, I'll help you. So he takes his old key. He was old, and he takes his key out and hits it, punches what floor? Floor 7. And I rode up the elevator with 106. How cool is that, right? But all that is a way to say, how do we go from 1 to 118 now counting in electrons? Now this to me sets a foundation of something so important, because we're going to get into bonding theories real soon. You're going to start to get into things like frontier molecular orbital theory. You're going to get into bonding theory, hybridization. How do electrons come together to form bonds? And then how can I break bonds? How do bonds form? How do bonds break? And so to me, this is really, really crucial for a good understanding, a solid understanding of chemistry. Not just general chemistry, all of chemistry, which then leads to biochemistry, which then leads to biology, okay? So to me, this is one of those foundational class lectures, foundational chapters that I personally really enjoy because I love geeking out a little bit in the quantum side of things. I really like the practical side of what we're learning out of this, okay? So let's jump into I'd love to jump into photochemistry. Let's jump into electron structure of atoms. Now, if you've had chemistry before, you're going to remember this as 1s2, 2s2, 2p2, blah, blah, blah. Some of you might remember those beautiful things. That's what we're going to be deriving. Where do the electrons go, and why do they go there? What are energy levels? Why is the 1s lower than the 2s? Why does the 2s have one node and the 1s has no node? What's a node? Are those little elf things? No, they're an actual zero probability of finding the electron. Okay? So we're going to talk about some really fun things here, real fundamental things for chemistry. Now, like I said, we're at that interplay between photons and electrons. So we have to geek out a little bit in the physics realm in order to understand what is a photon and what is this energy thing that we're really talking about. Because this whole chapter deals with energy. Low energy to high energy. The reason why blue looks so pretty is because it is being excited. The electrons in that shirt are being excited to an excited state. And what do I mean by excited state? Well, if I pump energy into an electron, it excites it and it moves to another orbital. When that electron comes back down, it appears blue, it appears yellow, it appears color. Just like this, red down here is like an orange color. You can see this because it's actually related to beta carotene, which is orange. Okay, so we see this very thin line of electromagnetic radiation that we call the visible realm. All right. Now, if we could see the entire spectrum, not just the visible spectrum, right now you would be seeing all your cell phones talking to the cell towers. Right now you would see all the earthquakes. They're massive, big, rolling. Right now you would see you would actually see all of the nuclear reactions going on the bricks right now, because these have lead in them. It's just natural to the brick, and they actually shoot off beta particles and some gamma particles as well. Not much, not enough to kill you or hurt you. But you'd be able to see those firing off the bricks right now. You can't, but they are. Trust me, we've actually put a Geiger counter on that and count them. It's kind of cool. It actually happens. So you might want to sit away from the bricks. Sasha, just FYI. It's not enough to hurt you. I do have some gamma in the lab that I'll show you when we get to nuclear, and it lights the class up. It's pretty cool. It's not really good for us, but it's fun. But anyway, we have these, really high energy up here, really fast, really short wavelength, really fast moving, or short frequencies, and down here these big rolling. Okay, they're all going at the speed of light, but it's just their amplitude that changes, and it gives us this what we call the electromagnetic spectrum. Okay, I use down here in the lab. In the laboratory, we have what's called a nuclear magnetic resonance spectroscopy. When you get to organic chemistry, you can play with that. That's dealing with radio frequencies. So it's not super high energy, but we excite little carbon hydrogen systems with radio frequencies. And so we hit it, and it goes out of plane, and we see how long does it take for it to come back into plane. And depending on how long it takes, gives us a spectrum. The longer, the slower, the further upfield, the quicker, the closer upfield. That's why we get a breakdown of spectrum. And we can use this technology in powerful, exciting ways. You know it as an MRI. That's all it is. Instead of spinning the sample inside of a magnet, you spin the magnet around the sample or the person. Okay? And so that's the technology that we're using. That's down here in the radio wave frequency. Really cool stuff, really practical stuff in the real world. Okay? So we have a wavelength and an amplitude. I'm not going to have you do a bunch of physics problems in calculating wavelengths. That's not the goal of this chapter. I will remove those from achieve because it's not what I'm trying to teach you. What I'm trying to teach you is what is the electron, what is the electron doing? How do we excite the electron? And what does it mean to have an excited electron, okay? Now, we make an assumption that the speed of light is 3.0 times 10 to the 8 meters per second. If you've ever heard of Einstein's theory of relativity, his theory of relativity is relative to an assumption. People don't know that assumption. Most scientists don't know that assumption. The assumption is that the speed of light has been 3.0 times 10 to the 8 meters per second times 0. Personally, I don't think that's a great assumption, and I think we're seeing violations of that. That has metaphysical consequences, but we'll talk about that. If anybody ever wants to talk about that on a free-for-all Friday, I'd love to do that, okay? So we know that the speed of light is consistent with, again, if you look at the wavelength and the frequencies, the wavelength and the frequency are what we really use for our calculations in these, all right? So we're talking about photons exciting electrons. We're exciting electrons, and we're gonna add energy to those electrons, and they're gonna move to a different frequency. Okay? Cool? Photons, electrons. All right. So one of the big mysteries of science, the one they called a paradox, was the fact that when you heat metal, when you add energy, think of thermo, when you add energy to metal, it gives off photons. Why in the world would heating of metal give off photons? That was a real conundrum in the turn of the 19th century. What was going on there? Because if you use the conventional understanding of matter, it didn't make sense. This is where quantum actually comes from. Some of the original minds trying to put this together and figure this thing out. And so why is it that we heat this metal and it produces photons? Very, very interesting. The big answer that comes through an incredible amount of research, incredible amount of physics and math, is this idea of quantization. Now, if you're following along in this class on my love of philosophy, faith, and science, the interplay of those three, resolving the tension between those three, wrestling with the tension between those three, I'm fine with that. Quantum is one of those metaphysical phenomena that should blow our minds. The reason why it should blow our minds is this. It tells me that the universe has been programmed. And you might be asking why. It's because the universe is digital, not analog. Think about that for a second. My daughter and I have this ongoing debate. She plays both the violin and the piano, and she's actually quite good at both. I'm proud of her. I, on the other hand, play the drums and keyboard, the piano. I've played classical piano for like 15 years of my life. Okay. Then I discovered Van Halen, and now all I do is geek out on the keyboard, which is super fun. The drums really fun to play, really loud metal. So with that, you have two very different instruments. And she makes the argument that the violin is way harder than the piano. I make the argument that no, because you're actually using all 10 fingers and 2 feet, the piano's harder than the violin. Because all the right hand's doing, by the way, is holding the bow. And she said, no, Daddy, that's not true. It is so much more difficult. And she proved it to me, but I was really impressed. She said, here you go. I want you to practice for 3 weeks learning Twinkle, Twinkle, Little Star. I want you to learn on the piano, and I want you to learn it on the violin. And after 3 weeks, I want you to tell me which one's more difficult to learn. Wow. I still can't play Twinkle, Twinkle, Little Star on the violin. And Twinkle, Twinkle, Little Star is really easy to play on the piano. You know why? Because the piano is quantized. The violin is analog. The piano is digital. So, here's what you need to be thinking about. What's the difference between a digital and an analog instrument? How many know what a trombone is? Do you think that's digital or analog? Can you make a sound on a trombone between C and D? Yeah. Can you make that sound on a violin? Yeah. In fact, you spend a lot of times try not to make that sound. You actually try to make the true C, and you learn how to, I guess my daughter does it, her mom teaches my daughter, learning how to resonate that to get it to come into being a C, not that weird sound in between. But you cannot make that sound on a trumpet. Trumpet, you either make the C or you make the B, right? So that's the difference between analog and digital. Now here's the deal. If the universe is digital, it means that it had a programmer. If it's analog, it doesn't need a programmer. But it turns out it is digital. And this was such a revolutionary idea in the 1920s, 1930s that people were really kind of losing their lunch over, because they realized what that implication meant. Now we've lost that. People don't talk about this today because we assume that it all happened by chance. It's all out of nothing, everything came, right? In the beginning there was nothing, it exploded, and now we have the money. Okay, cool, great story. So we don't even go back to the idea of, wow, the actual fundamental nature of the universe is quantized, it's digital, and here's what happens. Because it's digital, it means that there are only certain discrete energies allowed in our chemistry lab. Now this is mind-blowing, and again, I use these two instruments to try to get this across. You know what I'm going to do on my next set of slides? I'm going to put the OVX up there, the actual keyboard that Van Halen played jungle. That'd be really cool to have up there. Okay, so with that, violin, you can literally have any sound along the fretboard, right? But the piano you can't. You can make some bad noises with the piano, but you can't play the sound that's between wherever you're plucking that string, okay? And what happens with that is, because we have this quantized universe, here's the deal. When you look at this is bizarre. In fact, if you want to geek out, if you want a really fun read, especially chemistry majors, Google the book Alice in Quantum Land. It is the coolest analogy of what it would really be like to live in the quantum world. Because here's what happens. If I am going to move from here and exit the classroom, what do? Well, I just walk out the door. But if the electron wants to move from one state to the next state, it doesn't just walk out the door. It disappears here and it reappears over there. Huh? That makes no sense. Where is it going when it disappears? Why is it disappearing? What's it doing when it only exists there or here? It does not exist in between. And we're not comfortable with that. You might look at a pendulum, right? A pendulum. If you look at a pendulum in the macro scale, it looks like it's just swinging. But it's not just swinging. It's going dun, 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 at very discrete intervals. It's like the whole thing's disappearing and then reappearing, disappearing and reappearing. What? This makes no sense, exactly, because we can't take an analog idea and move it into the quantum world. Quantum is one of those things we accept as true. Why? Well, because we do have things called iPods. And they assume quantum to be true, and therefore technology came from the theory of quantization, and lo and behold, it actually does work. Okay? Are there other theories of matter? Absolutely. Absolutely. Spinning ring theory. I explained that to you in chapter 1, I think it was chapter 2. All right? But we assume, again, these energy levels. Even this idea of a tennis ball going downstairs is incorrect. The tennis ball does not cross. The tennis ball just goes funk, 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 funk. The electron doesn't. It's here. It's not here. It's there. It's not there. It's here. It's not there. It's here. It doesn't cross. It's like, I'm here, 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 here. Oh, I'm here, 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 here. Oh, I'm here, here, here. It doesn't cross. It's weird. It's just weird. All right? But what that tells me is that the universe has a discrete program in that it's quantized to certain levels of energy. That's fascinating, by the way. All right? Again, it's a piano. It's not a violin. Okay? And if it happened by chance, it should be a violin, not a piano. So it's one of those fundamental questions of why is it digital? Why are we in a quantized world? And that's actually, to me, a really important question. Okay? Two people debated this back and forth, Hooke and Newton, and they both had awesome hair. They also were probably both wearing wigs, so it's no fair. I think I'm gonna bring back the wig. I'm gonna come into class someday with a wig. I should actually wear a wig on this lecture, just so I could look like one of these guys. Wouldn't that be awesome? Just like, I'd be like, oh, flipping it back and just watch my wife do that all the time. Like, it'd be so cool to have hair that you have to flick back, and she moves it behind her ears all the time. Like, that'd be so cool. But anyway, I digress. So Newton thought that argued that light were particles because he's coming out of Newtonian physics. Right? That's what he would be teaching, Newtonian physics. And that tells me that just like the moon revolving around the Earth, okay, the electrons would be revolving around the atom. But here's the problem with that. If Newtonian physics were correct for the atom, the universe would not exist. The universe would collapse in on itself. Why? It's because that every time the moon goes around the Earth, it loses a little bit of its energy to the Earth. And so the moon actually gets a little bit closer. The Earth is pulling it towards it over time. It's not much, but it's moving it towards it, right? If you have that at the atomic scale, if the nucleus, every time the electron orbited around the nucleus, the atom slowly brought it in, then over time, everything would be nuclei, right? And the universe would be about a cup and a half of matter. Now, because it's not, this Newtonian physics for the explanation of the atom didn't work. And that's why Hooke said, no, light is not a particle, light is a wave. So there was this debate, is light a particle or is light a wave? And you guys probably know the answer is both. All right, this is one of the great paradoxes. How can light be both a particle and a wave? It has wave-like properties, but it actually has particle-like properties called photons. Okay? And this is one of those big kind of conundrum, kind of puzzles, back trying to figure out why, the nature of reality. What is light? What is matter? What are electrons? What are these things? And it was really Einstein who resolved the tension between these two. And he resolved these with this famous equation, energy equals h nu. Okay? And you see that h here is Planck's constant. And you might be asking me, what is Planck's constant? Why is that a big deal? Oh, it's a huge deal. Planck's constant is the amount of energy that an electron can move. There's your quantization. There is the amount of the piano, if you will, of the universe. You don't have energy in between Planck's constant. It is only in those discrete quanta that the electron exists. And that to me is a fascinating thing. There you see it, 6.63 times 10 to the minus 34 joules per second, or joule seconds, okay? Now, what's crazy about reality is if you get down to about 1 times 10 to the minus 40 centimeters, you actually lose locale in the universe. The whole thing becomes what they call the like boson-Higgs type of understanding of reality. It's just a weird, everything's like this weird wave-ish thing. But because we're bigger than that, we actually don't live at that level. We don't see it that way. We see it as electrons being excited by photons at a more practical level, like the pendulum swinging. We can actually see the pendulum swinging, not the pendulum in its quantized states. So, in quantum mechanics, and a couple of you in this class will have quantum mechanics, which is a super cool class. I love quantum. You can see that there are two ways to think of light, and that is as a wave or as a particle. And certain things are explained as light being a wave, and other things, the photoelectric effect being the big one, that is explained only through the particle. Okay, that light is a particle. All right, and that's the photoelectric effect. The photoelectric effect is what I just said. When you heat up a metal, it gives off light. It gives off photons. And why is that? And the photoelectric effect really was what was Einstein's kind of his big aha in explaining that in this quantized state. Now, this is kind of a fun little exercise. I'm just going to walk you through this. We've got a couple minutes left here, and we'll call it a week. When you actually look at, I'm going to show you how. So I think this is really cool. But they're really fast. I don't know if you see it. Is that What are you doing? Okay. So watch this. Okay, so I'm gonna pause this. So what's happening here is you're seeing how a photon or a particle. Okay, there we go. You can see that. All right. You know what? Hold on, I'm gonna pull a VLC. I hate Microsoft. Okay, so watch this. As this particle, okay, hits a boundary, what's happening to it? Well, you're seeing a particle become a wave. And so again, this is, and we'll develop this on Monday. We'll see the Schrödinger's equation, and we'll make it practical into the quantum numbers. But what you're seeing here is a particle becoming a wave when it hits a boundary. Okay? And it's one of those ways that you can see that, oh, okay, I can see that it's a particle and it's also a wave. It's just one way to visualize that it's actually both. It's not one or the other, it's both. And it really is one of those kind of conundrums of science that, wow, it just really is kind of weird because it just doesn't make sense, but we accept it to be true. And so you're seeing that, and again, this is the effect that we have when a photon becomes a wave. And there's a couple other ones. I'll just play them real quick and then we'll get out of here. But you can see that here when it hits a round, oh, I haven't both pulled up. But you can see when it hits that round barrier, what does it do? You can see the wave reflecting around that stationary state. Okay, I will pick this up on Friday. You guys have a fantastic weekend, and